Okay, so we're starting with immunity. We were just talking about the lymphatic system and how it's going to help pull interstitial fluid that was leaked out of the capillaries, and then we're going to comb it as it moves through these ducts and through nodes, and how the spleen does this for the blood. Let's talk about the nitty gritty, the immune system. And it's all about fighting pathogens. That's anything that causes infection. Disease causing agents like bacteria, virus, protozoa, um, which are single celled organisms, and then even fungal spores. The presence and multiplication of a pathogen, if unchecked, can cause an infection, and so that's what the immune system's working against to reduce infection. So, what is immunity? And a lot of people use this word incorrectly. Immunity is the ability of the body to prevent pathogen entry or destroy pathogen that enters the body. Um, I've heard of people like some people are naturally resistant to get certain diseases. It doesn't mean they're immune because they've never been in contact with it before. So, this is building immunity means you come into contact with the pathogen, your body learns how to fight it, and you're better equipped the next time you come into contact with it. There are two divisions, two types of immunity. There's innate and adaptive immunity. Innate means under genetic control, you're born with it. And this is a non-specific defense, meaning it's going to defend against anything that's not you. It's very general. Um, for example, if your body's this castle and you build this huge wall around it, the wall is just keeping everything out, or at least trying to. It's not specifically keeping a type of person or animal or whatever out. It's just trying to protect it from whatever, everything. And so that's going to be your innate defenses. You're born with those. And so we'll talk about what that means. And then the more complex type of immunity is your adaptive immunity, and it is very specific. And this is how this is how vaccinations work. Is they're really specific for an antigen, and so lymphocytes. This is going to be your B cells, your T cells. We just talked about how T cells mature in the thymus. So these lymphocytes are going to be very specific on who they're going to target and attack to help fight these foreign things for you. So let's start with our first line of defense, our innate defense. And like I said, this is non-specific immunity. And so we have these mechanical barriers. So, what keeps foreign things out? Your skin, mucous membranes, snot, earwax, tears, all of these things keep foreign stuff out of the body. We're trying to keep from having an infection. And so, this is the first line of defense. They give some great examples. As epidermis cells slough off, you remove superficial bacteria. However, I do want to say bacteria on your skin is a good thing. You have your natural flora and fauna of bacteria that help fight disease. So don't freak out about bacteria being on you. You need some to survive. But ciliated epithelium in your respiratory tract. So when you cough and you sweep things up, hair in your nostrils and your ears, like I mentioned already, tears, even your saliva, even urine, sweat, all of these things are non specific. Another defense that's actually once the pathogen gets inside, so you've broken through that first line of defense, that barrier, that mechanical defense, you have something called inflammation. And if something's inflamed, oh my gosh, you know it because it's red, it's swollen, it's hot, and it's painful. It's red because the blood vessels have dilated and they're bringing more red blood cells and more white blood cells to that area of infection. The swelling is because of all that capillary permeability and fluids being lost. Heat because blood is made of water and carries heat, and it's painful because there's a lot of pressure there. So you're hitting these pressure sensors and pain sensors. And this is a way to wall off infection site, and it brings more blood to the site, and where there's blood there's white blood cells. And remember, white blood cells can gather here, and that's what's going to destroy the pathogens. So these are the macrophages, that all the different phagocytes that will come and eat up any of the bacteria that got in on this cut or whatever. Exudate, I can't even speak, exudates fluid that contains fibrinogen and other clotting factors. So this is where we're going to start making, a clot and a scab, so that we keep any more bacteria from coming in. And we're just going to destroy these pathogens and try to keep them from spreading. Any cells underneath that were damaged will be replaced. So here is the inflammatory response. Your blood vessels dilate, capillary permeability increase, so the fluid leaks into this space, so white blood cells can invade there. Tissue starts clotting, fibroblasts arrive, phagocytes are actively eating anything, and your cells are dividing, repairing themselves. Another thing that's still innate defense, so it's still non-specific, are these chemical barriers. Chemical warfare that's happening inside your body once something's gotten through the hair and the skin and all of that. There's enzymes, interferons, and then the complement system. So enzymes are in body fluids, and for example, pepsin is in a gastric juice, and lysozymes are in your tears that help destroy microorganisms from getting into the spaces of your eye. So you've got these enzymes that can speed up chemical reactions and help destroy pathogens. Interferons are usually just for viruses, and so what these interferons do, a damaged cell or a virally infected cell will release the interferon, and it will tell all cells around that there's a virus nearby, and they'll kind of put up a defense mechanism to block out themselves from getting infected by the virus. This can help act against tumor growth, and it also does communicate to phagocytes to comb that area. The complement system is a group of proteins. I want to say there's like 21 of them, and they all help stimulate inflammation, attract phagocytes, and help destroy pathogens. And then there's natural killer cells. And I love these cells because they just sound really mean and like fierce. And you're born with them. And it's just a small group of these lymphocytes that defend against virus and cancer cells by releasing what's called perforin. And perforin does what it sounds like. Perforate means to poke holes. So it pokes holes in the cell membrane, and the cell lyses, which means breaks. And it actually kind of, when you poke a hole in the cell, water flows into the cell very quickly. It kind of explodes like a water balloon. And natural killer cells also enhance that inflammatory response. Still in innate defense, so still in non-specific immunity, we have phagocytosis. Remember, osis means a condition of, cyte is cell, phage means to eat. So this is a process of cells doing a lot of eating, and they're what's going to remove anything that's foreign, that's not you, that was found in the lymph or that was found in the blood. And they're most active. The most active phagocytes are our neutrophils and our monocytes. We've discussed those in our blood unit. Chemicals from damaged tissues attract them. This is called chemotaxis. Chemical and taxis means to attract. So this would be positive chemotaxis. Monocytes that leave the blood can become those macrophages, those large eaters, and then they can move around, right, throughout the tissue and comb for foreign antigens. And then your mononuclear phagocytic system consists of monocytes, which is why they call it mono, and macrophages, which is why they're calling it the phagocytic system. These are just collectively what that's called. When you're talking about monocytes and macrophages, you're talking about the mononuclear phagocytic system. Another defense that is non-specific, you'll get this not from one type of bacteria, but from all of them, is or virus, you might experience fever. And so fever is just increasing the thermoregulation point of your body. And so you're going to get hotter. And it's all because of this interleukin 1. And that's called an endogenous pyrogen. Pyro means fire. So it's from within and it generates fire. So fire maker from within. And your body gets elevated. And what does this do? This actually helps slow down the microbial growth, but actually speeds up some of the enzymes that help fight against these foreign invaders. It will cause your liver and your spleen to take up more iron. It makes it available for bacteria and fungi to use their normal metabolism. And then, so like you're stopping the pathogen from working, but you're working at an elevated speed. So this is increasing your phagocytic activity. I've known this forever, that a fever means you have an infection, and that fever is not necessarily bad, because look what it's doing. It's inhibiting microbial growth and speeding up the immune system. And so as a mother, I remember when my child was very young and he had just a slight fever, first thing I wanted to do was lower the fever because he was uncomfortable. And then I'd have to remind myself that a low-grade fever isn't the worst thing in the world. It's actually part of the natural immune system. So here are your types of innate. Remember that they're non-specific defense mechanisms. So let's get into the adaptive or the specific defense mechanism. And so an adaptive defense mechanism is you're gonna build this. So this is your third line of defense. So the first line was the physical barrier. The second line was the chemical barrier, and this is the last. This is the last straw. You're going to go all out to fight this pathogen because it's already got through all the barriers, plus all the inflammatory response, the natural killers, the macrophages. This is your last chance really to fight off this infection before it takes you over. So it is going to be particular. It's going to be very specific to a different pathogen or some toxin. And the real important thing here is this is all based on the ability to distinguish molecules that are not part of your body and compare it to all the molecules that you do have. And they call this recognizing self from non-self. An antigen is a not self molecule that can evoke an immune response. And we mentioned these when we looked at blood typing and RH, and we talked about like the blood type A has the A antigen on it, and blood type AB has both A and B proteins or glycoproteins. Those could be antigens to somebody who has O, because that is not self molecule, so that's going to evoke an immune response. Adaptive responses are carried out by lymphocytes and macrophages that help recognize, again, specific antigens. And so this further divides. So we are dividing immunity into innate and adaptive. And now we're taking that adaptive immunity and dividing that into cellular and humoral response. Now, cellular is going to be performed by immune cells, and it's actually going to destroy cells, where humoral immunity is it's going to be lymphocytes, but they're making antibodies. And so, if you need a way to remember this, I think of humoral as funny. And so, in humoral immune response, there's nothing being killed here. It's antibodies being formed, but nothing's being destroyed. Where the cell immune response, that's where the cell is being destroyed. And so, I that helped me when I was studying anatomy and immunology. So as the pathogen enters your body, it gets that first barrier, right? And then it passes that. So now it's in, and your second line of defense is there, and your third line of defense is there. Don't think that like first your second line of defense is going to work, and then it's going to stop if it didn't work, and the third line. They're working together at the same time, but the third line of defense is specific where your second line of defense is not. So we already said antigens are these molecules that are foreign, so they're not yourself. And your lymphocytes, these white blood cells, these B cells and T cells, have receptors on their surface that can recognize these antigens. And antigens could be any of these molecules that are found on the outside of the membrane. So where do they originate? Well, lymphocytes are produced throughout all of your life, starting before you're born. And you do have T lymphocytes and B lymphocytes, which I call T cells and B cells. Both of these are made in the bone marrow, but T cells matured in the thymus, and B cells stayed in the bone marrow and matured there. And it says after release from the thymus, they make up about 70 to 80% of your lymphocytes, your T cells, and B cells are a fewer amount. And so you can see where they differentiated, where they matured. So they were made in the red bone marrow and matured in different places, and then where you'll find them and what their function is. So remember I said the humoral immunity is going to be with B cells, and they make antibodies. Where T cells mature in the thymus, that's where we're going to actually come into contact with cells and destroy them. So this book starts with T cells. I usually start with B cells, but it doesn't matter. They work hand in hand. So we're going to activate a T cell with an antigen presenting cell. And so usually this is some type of macrophage or phagocytic cell, like a monocyte that has engulfed a foreign antigen, destroyed it with the enzymes, and then it's going to actually poke a piece of the the protein, the antigen fragment, out of its cell membrane. And now it's presenting the cell. So it's like a phagocyte ate something bad and said, hey, look what I just ate. I need to show you this. It's talking to a T cell so that you know what to look for and to destroy it. So the APC stands for antigen presenting cell. So it ate the antigen, it digests it, it's displaying it on its membrane, and it's using that. I think of like in Lion King where he holds up Simba. He's displaying Simba to everybody. That's always how I picture an antigen presenting cell presenting an antigen. Well, his arms is the major histocompatibility complex. It's the protein that's pushing the antigen fragment out to display it. So once that T cell encounters the antigen presenting cell, displaying that little fragment, it recognizes that antigen as foreign and it's looking for it. It's activated. And so it will secrete polypeptides called cytokines. Cytocell kines is like protein chemicals that enhance some cell responses to antigens. There's a bunch of different cytokines, and we'll see a picture of that in a little bit. So here's the specialized T cells. So when a T cell gets activated, it does do proliferation and differentiation. So it makes a whole lot of clones of itself, but it also differentiates them a little bit. So you have helper T cells. Helper T cell you've probably heard of before. Helper T cells are the one cell that communicates with both the B cells and other T cells. So that means they're talking to the cellular response and the humoral response. Cytotoxic T cells attack virus or cancer cells. So think of this word cyto, cell, toxic. So it's cells that have gone bad. It's your own cells that need to be destroyed. And then memory T cells remember the antigen that it got activated with, and it's looking for future infection or future cancers of those types of cells. And so this is how you're building your immune response, is with those memory T cells. B cells can be activated also when an antigen fits the shape of their own receptor and they bind to them. And B cells, by the way, can be an antigen presenting cell. They can bring in the cell, but a lot of times the B cell just needs to bind with the whole antigen on its receptor, and then it gets activated by cytokines from the T cells, those protein chemicals released. And once that is released from a helper T cell, the B cell starts proliferating and differentiating. And so remember, that just means making many clones of itself and kind of differentiating between two types. Some of those types are going to be memory B cells, which look for more of that same antigen. So here's the story. You got a bacteria into your body, and a B cell has a receptor that is the correct shape for a protein on that bacteria. And that tells, remember, all these receptors are looking for foreign things, these antigens. So it's bound and it's gotten activated by these cytokines. That bound B cell with its antigen starts making a whole lot more B cells. And those memory B cells are going to stick around for sometimes years looking for that same bacteria to help fight. But other B cells differentiate into plasma B cells. And what the plasma B cells is, they make the exact same receptor, except it's missing the a piece of the receptor that goes through the membrane. And so it can't stick on the membrane, so the little piece of receptor floats off. It is released out of the cell, and these are called antibodies. And the science word for antibodies is immunoglobulins. It's weird, the word antibodies, to me, because anti means against and body sounds like my body, but these are for your body. And so I actually kind of like the word immunoglobulin better, because there are these little globular protein things that are floating around in your tissue, and what they'll do is they'll stick to the exact same bacteria that the original B cell discovered. And so remember, they're looking for this specific shape. And antibodies or immunoglobulins are carried by your blood and body fluid, and so they're going to go to this infection site and they're going to do the humoral response, an antibody immune response. And what they do is they stick on to these foreign antigens, kind of like sticky notes that say, hey, this is a bad thing. So let's see if this picture helps you out a little bit. So here you have a macrophage, and it's eating this bacteria, and it's used enzymes and a lysosome to break that down, and then it's used its MHC molecule to present that little fragment of that bacteria. So here it's displaying that with the little MHC molecule. Excuse me. So a few things can happen. It can talk to the helper T cell, and the helper T cell can make copies of itself and start releasing chemicals. Some of those chemicals are going to talk to B cells. Some of those chemicals are going to talk to cytotoxic T cells. The cytotoxic T cell gets activated, and what it does is it makes many copies of itself. Some of them memory T cells, some of them cytotoxic T cells. Remember, we said there were 3 types of T cells, so here they are. And the helper T cell is the only cell that can talk to both humoral and cell-mediated response. So that's going to be important. The cytotoxic T cell makes active cytotoxic T cells and then memory T cells. And so they have the exact same little receptor shape as the original one. So this is saying, hey, something bad I just ate, you need to go look for cells infected with this. And that's what these are going to go do. They're going to look for cells that are infected with it. And if they find one, they're going to tell that cell, they're going to release perforin, and they're going to tell that cell to kill itself. And the cell's going to listen. That's crazy. This is great because everybody right now has cancer cells. But if you have a strong immune system, your cytotoxic T cells will discover those cancer cells, because cancer is your cell gone bad. And a lot of times those cancer cells are going to have antigens on the outside. And your cytotoxic T cell will discover that, and it will actually tell your cancer cell to kill itself so that it doesn't divide and become a tumor. B cells, so here's your B cell, and it has these Y-shaped receptors. If you'll notice this, see it has a Y-shaped receptor. T cells have an I-shaped receptor. So these B cells on their little receptors, they can bind to the whole antigen. So it has a specific shape there, and the antigens, proteins there, and they match up. And when they get activated by these cytokines, it will proliferate and differentiate. And it'll make memory B cells, but it'll also make plasma B cells. And I don't know why that's not in this picture. But in a plasma B cell, these little receptors are going to be made, but they're not going to have that inner membrane receptor region, and so they're going to float off as immunoglobulins. So kind of here's a picture of that. So here is the plasma B cell, this active B cell that's releasing the immunoglobulins, the antibodies, and then here's the memory ones. And I think this is just showing, like, I'm not sure why we have 2 things going on. Plasma cell. Yeah. So the B cell makes, remember, it's part of the humoral response. It's very specific to a type of antigen, and it creates antibodies. The antibodies are going to mark foreign proteins, foreign cells for destruction. T cells, helper T cells communicate to humoral and cell-mediated responses to inform them about what antigens in the area. Cytotoxic T cell will kill virus-infected or cancer cells, and the memory cells will look for those same antigens for years to come. So let's look at the antibody or the immunoglobulin that the B cell makes. It is a globular protein, which is why they call it immunoglobulin, and it is a Y-shaped. It's made of 2 heavy chains of amino acids and 2 light chains. They're held together by bonds. And each one is unique at its antigen binding site. And there are 5 major types of immunoglobulins, and you do need to learn these. So there's IgG. So Ig stands for immunoglobulin. That's just the type of antibody it is. So there's GAMED. If you rearrange that, it's GAMED, and so it's gamed. I don't know if you're a gamer, but the bad guy's been gamed. I don't know. I'm trying to think of a way for you to remember that. And it helps you know the percentage of them. And so it doesn't matter if you switch that E and that D because they're both less than 1%. So the G antibodies act on bacteria, viruses, and toxins. The A bodies are found in your exocrine gland secretions, so your tears and sweat glands. The M is going to look on antigens found in your food and in bacteria. D, well, let's go in order like we're learning. E, exocrine gland secretions also. And that can also be like milk secretions. And then D, found on B cell surfaces, and we'll see that in infants. And so here is a picture of an antibody. So these are the heavy chains, and then these are the lighter chains. And these are disulfide bridges that are holding, these are the bonds, covalent bonds between sulfurs, holding them together. And so this is the shape. And if this were a receptor on a B cell, it would have another piece to it down here that allowed it to go through the membrane. But when the plasma B cell starts making these, that piece is missing, so they don't stick in the membrane and they float off. Right here is the most important part. All of these antibodies look exactly the same right here, but up at the ends of this Y are the antigen binding sites. This is the shape that matters because this is the one that's specific for the shape of the antigen that we're looking for. And so immunoglobulins, GAMED. So what do? Well, they agglutinate, precipitate, and neutralize. So what the crap is that? Well, agglutinate is clump them together. We saw this before with blood. And so if you think about this, it just clumps them together. Each antibody can hold 2 antigens, and so you can start easily clumping them together. Precipitate means it makes the antigens insoluble, and so it's going to pull them out of fluid more to a solid, and that also makes the phagocytes find it easier and digest it. You know, I think about this. If you're fighting a war, don't you want a lot of your bad guys in the same place before you send attack on them? Like, it's easier to group them together and then have a huge macrophage just come in and gobble them all up. And neutralization just means the antigen covers the whole thing, and now they can't divide. Antibodies also activate that complement system. And so we talked about these are proteins that fight. And so all of that stuff. Not the most important thing, but that they activate the complement system. And then they stimulate local inflammation. And again, so all of this antibodies, gathers up the harmful things to be gobbled up, gets the complement system going, helps inflammation happen, and so that we can fight this foreign antigen. So what is immunotherapy? This is when you use the immune system to fight disease. And so, like, you've probably heard of monoclonal antibodies. So a specific B cell will produce a single type of antibody, that's monoclonal, and it'll be fused with a cancer cell, and so they'll produce a cell that produces this one type of antibody, and cancer is uncontrolled growth, so it's just going to keep dividing. And so they use that in a lot of places. And then we also use cytokines to treat different diseases. So if you've heard of immunotherapy, it's using components of the immune system fight new diseases. So in our immune response, we talked about there's innate immunity and then there's adaptive immunity. And in innate immunity, it was non-specific. It was our first and second line of defense, and we were fighting any antigen. In our third line of defense was our adaptive immunity, and it's very specific. Within that adaptive immunity, we divided it into the humoral response and the cell-mediated response. And the humoral response included B cells, and the cell-mediated response included T cells. And T cells fight off and kill infected cells. The B cells differentiate into plasma B cells and make antibodies to clump things together. And then the helper T cells kind of in the middle, communicating with both. So that's pretty much immunity. Now, when I talk about primary immune response, it's the process of first coming into contact with this antigen. And so you're going to actually feel sick from this. Whatever I've come into contact is the first time I've come into contact with it. And so my B and T cells are just now getting activated, and my plasma cells are releasing immunoglobulins to fight this. And it's going to take 5 to 10 days for my antibodies to start appearing in my blood. Also at this time, memory B cells are being produced. Your secondary immune response is when I come back. So let's say in 6 months, I come into contact with whatever this is that I'm sick with now. Well, what do I have in 6 months that I didn't have, 5 days ago? Well, I have those memory B cells, and I don't have just one or two. I have lots of them. And so it's like an army that's already prepared to fight this antigen because we've already been in contact with it before. And so what you see is a super high concentration of antibodies made really quick. And it makes even more memory B and more memory T cells. And so each time you come into contact with it, you build immunity. And your antibodies can remain for months or years, but honestly, they're just proteins, and so they degrade. And remember, if we're clumping them, using them to clump antigens together, and then a macrophage is eating them, they're going to get broken down pretty quickly. The memory cells, though, they do live for years. So let's look at this graph. This is showing the antibody concentration in your plasma. Remember, that's the fluid of your blood. So you don't have any at first because you've never come in contact with this and you're not sick. So you get exposed to a foreign antigen, and your B cells have recognized that, and they've started to proliferate and differentiate and make plasma cells and memory cells, and those plasma cells start cranking out immunoglobulins. And so this is the immunoglobulins being made, and you feel awful, but your immunoglobulins are communicating to your macrophage, and you're fighting the infection, and over time you start to feel better, and your immunoglobulins are slowly going down. Look at the difference with secondary immune response. After the second, third time, whatever, you get exposed to this, what do you have here? You have memory cells that were made in this primary response process. And so those memory cells act so much faster. They all start proliferating and differentiating, making immunoglobulins, and you can fight it so much faster. And guess what? You fight it so quickly, you may not even feel sick. You may not even know that you came into contact with that antigen again. Now, there's some practical classification of immunity on how you get it. And so we've been talking about naturally acquired immunity. And this means that you literally get the disease and you overcome it, and it happened naturally. You either got it from your mom, she was sick and you got the immunoglobulins, or you came in contact with it yourself. Artificially acquired, you had an injection. And so this is going to be like a vaccine. So when you get a vaccination, you get an attenuated virus, a weakened virus. And so your immune system sees the protein. It thinks, oh my gosh, we're under attack by a virus. And it builds your immune system. It builds those memory cells so that when you actually do come into contact with a live virus, um, a non-weakened virus, when you get infected, you have all those memory cells, right, that can work to make your immune response faster and you not feel sick from it. Passive immunity is a temporary immunity obtained via antibodies. So you're not being exposed to the antigen. You're not building an immune response. So passive is to me kind of lazy. So this is a vaccine would be where instead of you getting the live virus and building immunity to it, like that's active immunity, you're getting like anti-venom. When you get anti-venom, it's working, it's like a quick fix. It's all these antibodies to hurry up and discover the toxins in your body and break them down as quickly as you can. But you're not going to have any memory cells, so you're not going to be able to next time you get bit by a copperhead or whatever, you're not going to be immune and be able to like run and jump and play. You're going to have to go back and get more antivenom because you don't have any secondary immune response. Active immunity is where you are going to have the memory B cells. And so naturally acquired, you get sick or you get immune response naturally. So whether this be by getting infected yourself or through breastfeeding, and this usually comes in medicinal form. And so here's really, oh, I'm so sorry, I don't know what I did. This is a really good table to see naturally active and then artificial active, naturally passive, and artificially passive. And so I really like this this chart here. Hypersensitivity is an exaggerated immune response. So this is like allergies to a non-harmful antigen. I think about it as your like immune system kind of being dramatic. Some people are pre-sensitized. Some can affect any. Some it's an inherited ability. And there's 4 types of hypersensitivity. And so type 1, 2, 3, and 4. Immediate reaction, antibody dependent cytotoxic reaction, immune complex reaction, and the delayed reaction. And so, what is the immediate reaction? It's an overproduction of your immunoglobulins. An example of that's hay fever. In type 2, phagocytosis in the complement mediated system overacts and that or happens, and that could be like you got the wrong blood. Type 3 is when your phagocytosis and lysis aren't really clear on which complexes, and so this could actually result in autoimmunity, like maybe lupus or psoriasis or something. And then delayed reaction is where the T cells and macrophage release chemical factors in the skin, and you end up with dermatitis. It's important to go ahead and mention transplantation and tissue rejection because it has to do with the immune response. And when you have to do any tissue, we've already talked about blood transfusions. That's a tissue transplant. But also with other organs and other tissues, you need to make sure there's not a rejection. And so you're looking at MHC molecules and these antigens to make sure that the body is not going to create B cells or T cells that are going to respond to those shaped molecules. And so we have some different reactions into diseases here. When you do receive a donation of a tissue transplant or organ transplant, usually they are going to put you on some type of immunosuppressive drugs to keep you from rejecting that organ or tissue. Now, there are 2 types of, or 4 really types of tendencies for rejection. So there is autograph and isograph. Now let's look at that. So auto means self. So these are, your skin is used, you get a skin graft from your own skin, like from your leg, to replace another part of your body. You're not probably going to reject that because it came from yourself. An isograph, iso means same. So this is from an identical twin, and usually not also going to cause rejection because you have the same DNA, and so you're going to be making the same proteins, the same white blood cells, um, and so you wouldn't reject it. Now, allo means different. So this is some other person, an allograft, and a xenograft is very different. And so that would be from a different species, and this could cause rejection. This has a higher tendency, and so those are examples of the transplant types. Autoimmunity is when you attack yourself. So your immune system starts fighting your own tissues for whatever reason. It fails to determine what is self and what's non-self. Remember, that was so important. And they start producing bodies they call autoantibodies. They're antibodies that fight yourself. Cytotoxic T cells could attack your body tissues and organs and tell those tissues to die. And there's a couple disorders with these different types of cells, and they haven't really quite figured them all out. So here's quite the list of autoimmune disorders. One that interests me is lupus. A lot of people don't think about Graves' disease as an autoimmune disease. Type 1 diabetes. Where is... I don't see it. But even... I just lost the name. Don't you hate it when that happens? Arthritis. I don't see arthritis. Oh, there it is. Rheumatoid arthritis. That's a really common one. And so that's where the cells lining the joints are attacked by antibodies. So they're being told that they're foreign material and need to be destroyed. So let's talk about HIV and AIDS, because that's one of the most, that is the most well-known virus, and it's human immunodeficiency virus and acquired immunodeficiency syndrome. And AIDS is when you have AIDS when your white blood cells have reached a certain number, and when the white blood cells have been being made to fight secondary infections, and your secondary infections are just overcoming. You're getting these other infections, and you're not able to fight them, like simple things like colds or a cut or whatever. So HIV is the actual virus that causes this. And the problem with HIV that I really want you to know is it attacks the helper T cell. Now remember, with the helper T cell helped activate both the humoral response and the cell-mediated response. Those B cells and those T cells, they're not synchronized. And so the helper T cell is the major communicator between those two lines of defense in our specific immunity, in our adaptive immunity. So when you take out a helper T cell, you still have B cells and T cells trying to fight, but it's just not organized. So what happens is you lose your immune response against just common pathogens or cancers, and that's what you could die from. HIV and AIDS has come a long way as far as medical treatment against and protection against these people. And, it doesn't have to be sexual contact. It could be contaminated needles, even birth or milk from an infected mother. And then one of my close relatives actually contracted a similar disease due to blood transfusion. So how does your immune system change as you age? Well, we already mentioned that the thymus gland is going to shrink. It actually is replaced with adipose tissue. And the strength of your immune response decreases. You're at higher risk for infection and disease, cancer, T cells, those decrease slightly. Remember, we have 80% of our lymphocytes are T cells, so those numbers go down, and B cells that were there already low to begin with. Your response just becomes slower, so you might need extra doses of vaccines, and you might start making more autoantibodies, so you also might develop sensitivities to new things and have new allergens, and so it becomes a problem, right? But it's better than the alternative, I guess. And that is the end of this chapter, and we have covered the lymphatic system and the immune system.